Okay, so we'll revise linear control design, and to start the process of designing, we'll first set up the problem, and for that we'll first see a result which would help us to write down the gain factor and for a negative feedback loop. So firstly, so we'll see a cascade interconnection of LTI system. So here each mapping, for example, the block K and block P represent LTI system. So they could be a map, LCC ODE map, suppose. So they are LTI systems. Then we have seen that for LTI systems, the output can be related to the input using the relation. Uh, Output is convolution of input with the impulse response, and similarly in the Laplace transform, that is multiplication of E of s times, for the case of K block, it would be E of s times the transfer function HKS. Similarly, Y of s would be HP of s times the input to that, that is U of s. Now uh, representing y in terms of E would be Y of s equal to HPS, HKS, E of s. So we see that overall the system behaves like a multiplication block where input has been multiplied by some constant. So hence in frequency domain, LTI system can be a cascade interconnection, or uh, yeah, a cascade interconnection of LTI system can be thought of as a multiplication block. Now we'll use this to lay out the mapping from input to the output. So we'll see map from R to Y, R to E, R to U, and so on. So this is similar to the multiplication block we had done earlier, and we can easily get these three relations. Now a quick way to, suppose we require the map from R to Y. So a quick method could be, so suppose we need GR to Y, so we'll neglect the effect of NS. So we'll neglect these two. Now, so what we are left with is E equal to R minus Y, since there's no N. So K of E, that is K of R minus Y, that is U, and that directly goes to P. So P of K of R minus Y equal to Y, and in S domain that would be Y of S equal to P of S K of S times Rs minus Ys. Now rearranging Ys to get this, so we'll get the first term. So similarly we do the exercise for every mapping, and we get 9 maps in general. Now one aspect of control system which we discussed in previous class was BIBUS stability. Now we want the each signal, the each output at every stage to be within within our control, so it should not explode. So we want each map to be BIBUS stable, so that's one aspect. And we see 9 distinct maps, but number of distinct maps, for example these two are same, just the signs are different, so those are 4, and the fourth and third are related, that this plus this is 1. So if this is BIBUS stable, then this has to be BIBUS stable, and so on. So we are left with 3 maps to be made BIBUS stable, that is Pk by 1 plus Pk, P by 1 plus Pk, and Ka by 1 plus Pk, where each is represented in S domain. Now a general result is, um, all possibilities are to be considered. For example, uh, suppose one of the mapping, suppose one of the transfer function P of S or K of S is BIBO stable and the other is BIBO stable, then both of them are possible. It's possible that both are stable, then the interconnection is unstable. It's also possible that both are unstable and interconnection is stable. So these are some examples which show that all the possibilities are there, and hence we need to have consideration for individual problems. Now other aspects are, normally we majorly focus on two aspects: nominal stability of performance and robust stability performance. So we'll discuss individually in the next videos. Okay, thank you.